Okay. In this video, we'll be discussing, we'll briefly mention the different carboxylic acid derivatives, and then discuss acyl chlorides in a little more detail. So there are several derivatives of carboxylic acids that are all, we can make all of these different derivatives from a carboxylic acid, and we can convert them back to carboxylic acids. So the first and the most reactive is acyl chlorides. Then we have anhydrides. Esters. And amides. In fact, let me specify that this amide could be with R groups. It could have alkyl groups attached instead of just protons. Now, the reactivity of each of these different groups is controlled by how good their leaving groups are. And so the leaving group of the acyl chlorides will be this chlorine atom. For the anhydrides, it's a carboxylate ion. For the esters, it would be an alcohol. And for the amides, it would be an amine. And so the better leaving groups are the weaker bases. And so this chloride ion would be a very weak base, and so it's a very good leaving group, whereas an amine is a stronger base, and so it would be a very poor leaving group. And that's why acyl chlorides are the most reactive, and the amides are the least reactive. So as we go downwards on this list, we go from very reactive compounds to less reactive compounds. And because the acyl chlorides are most reactive, followed by the anhydrides, followed by the esters, followed by the amides, we can convert one group to another as long as we go down the list. So we can convert an acyl chloride to an anhydride, or an ester, or an amide, but it would be very difficult to go from amide to acyl chloride in one step. We would probably have to convert the amide back to a carboxylic acid, and then convert the carboxylic acid to the acyl chloride. And so it would be there'd be multiple steps involved, and it'd be a more difficult reaction to do. And so we've already used acyl chlorides in different reactions in the course, for example, of Friedel-Crafts acylation. And so we've already kind of gone over a little on how to make an acyl chloride. In general, there are three reagents that are commonly used in order to convert carboxylic acids to acyl chlorides that we most often discuss: thionyl chloride, but PCl3, phosphorus trichloride, or PCl5, phosphorus pentachloride, will also work to convert carboxylic acids to acyl chlorides. And so one example of what we can do with an acyl chloride is we can use it to form an amide. So we're going from the most reactive the acyl chloride, the most reactive on that list, down to the least reactive on that list for the amide. And in general, We'll take our acyl chloride. In this case, we'll react it with dimethylamine. So we have two methyl groups attached to our nitrogen. That will wind up with this amide with two methyl groups attached to our nitrogen. And the mechanism for this is fairly simple. Start with our acyl chloride. Then the lone pair of electrons on our amine can attack that carbonyl carbon and kick the electrons up to the oxygen. It will form this intermediate with negatively charged oxygen and a positively charged amine, positively charged nitrogen. And so the electrons from this oxygen can come back down. We'll kick off the chlorine as a chloride ion, so it's a good leaving group. We have a positively charged amide now. And so if we just deprotonate that amide using another dimethylamine as our base, then we'll get the dimethylamide as our final product. And so the reaction from an acyl chloride to any other carboxylic acid derivative will follow very similar mechanisms. That we could convert an acyl chloride to an anhydride by reacting it with a carboxylate ion. We could convert an acyl chloride to an ester by converting it by reacting it with an alcohol. That the book goes into a lot more detail on all of those different conversion mechanisms from acyl chlorides to the different carboxylic acid derivatives. But all of these mechanisms should be very similar, where we attack the carbonyl, we kick off the chlorine as our leaving group, and then we might have to protonate or deprotonate where appropriate in order to make the final product. So we can actually reduce an acyl chloride, and we'll go over that real quick. And if we react our acyl chloride with a strong reducing agent, such as lithium aluminum hydride, we'll convert the acyl chloride all the way to the alcohol. However, if we use a weaker reducing agent, milder conditions, such as diisobutyl aluminum hydride, followed by an acidic aqueous workup, then we can stop the reduction at the aldehyde. And so we can convert an acyl chloride to an alcohol or to an aldehyde depending on the reducing agent that we use. Again, strong reducing agents, we cannot stop at the aldehyde, it'll go all the way to the alcohol. Milder reducing agents, we can stop at the aldehyde. And the mechanism for this is also pretty simple. We'll just use lithium or the aluminum hydride from lithium aluminum hydride. If it were dibol H, it'd be very similar. The aluminum hydride bond, those electrons would attack the carbonyl, kick the electrons up to the oxygen, giving us a tetrahedral intermediate. The electrons from the oxygen can come back down, kick off the chlorine, and form our aldehyde. Now, if we were using a strong reducing agent, like lithium aluminum hydride, then that a second molecule of the aluminum hydride could attack that carbonyl and end up reducing it to the alcohol. But if we're using dibol H, then we would stop at the aldehyde, assuming that we use one equivalent of dibol H. If we use two equivalents, we'll still convert it to the alcohol. So we have to be very careful with the stoichiometry, but it is possible to use one equivalent of dibol H and get the aldehyde rather than the alcohol. We can also react acyl chlorides with organometallic reagents, such as alkyl lithiums or Grignard reagents. And what makes acyl chlorides a little different from reacting ketones and aldehydes with Grignard reagents is that we will get two reactions instead of one. And so rather than adding one alkyl group to our carbonyl carbon, we will add two alkyl groups and form the tertiary alcohol. So these two alkyl groups were added from the Grignard reagent, creating the two additions and creating the tertiary alcohol. And the mechanism for this are two additions from the Grignard reagent. We start with the acyl chloride. Our first Grignard reagent will attack that carbonyl carbon. So we have our first addition of that alkyl group. And then the electrons can come back down from this oxygen. We can kick off that chlorine. And form the ketone. Once we have the ketone, well, then we can react this ketone with another molecule of Grignard reagent. And then we simply have to protonate this oxygen in our acidic aqueous workup. To form the final tertiary alcohol product. So again, we can't really stop this reaction with the Grignard reagent. We can't stop at the ketone, because the ketone will react again with the Grignard reagent to form the tertiary alcohol. If we were using alkyl lithium reagents instead of Grignard reagents, we'd get the same result. But there is a way that we can stop at the ketone, and that's to use something called a Gilman reagent. And we won't go into the mechanism behind the Gilman reagent, but we will show how to produce a Gilman reagent. We require 2 alkyl lithiums. We react that with copper iodide, copper 1 iodide, and we'll get 2 R groups attached to a copper lithium complex plus lithium iodide. And this is our Gilman reagent. So once we have the Gilman reagent prepared, we can react that with an acyl chloride. So in this case, we'll use a dimethyl Gilman reagent. And that's the first step in the reaction. The second step in the reaction is water. And we'll add one of these methyls to our carbonyl. And so we'll replace this acyl chloride with the ketone. And we'll stop the reaction at the ketone rather than going all the way to the tertiary alcohol. So those are some of the reactions of acyl chlorides.